334 Chapter 15. Waves, Sound and Electromagnetic. And water waves? The photographs and sketches of springs and water waves serve as guides as we construct mental images of phenomena we can sense, but not necessarily see. We begin by looking at the two major categories of wave phenomena: mechanical waves and electromagnetic waves. By ordering waves according to frequency, the wave spectrum organizes the different types of waves within each of these categories. For each wave category, we will describe phenomena due to reflection, refraction, absorption, standing waves, and the Doppler effect. Sound will be used to illustrate mechanical waves. Light, microwaves, and radar will illustrate electromagnetic waves. Wave classification: sunburn, television, sound, jackhammer vibrations, radar, earthquakes, tsunami, and microwaves. Some of these phenomena are easier to imagine than others. Jackhammers and earthquakes shake the ground, and the ground shakes you. You can watch tsunami waves move across the ocean. Even sound seems quite real as you strum a guitar and feel the vibrating strings. By contrast, other phenomena seem more abstract. It is hard to imagine how energy travels from the sun to our bodies, from the television tower in the next city to that box in the living room, from the police car to your car. Light, television signals, radar, and microwaves seem almost magical. The two categories of waves, mechanical and electromagnetic, reflect our sense of the concrete and the abstract. Mechanical waves, sound, jackhammer vibrations, earthquakes, and tsunamis are all examples of mechanical waves, waves created when chunks of matter, vocal cords, hammers, rock, or water vibrate. This matter collides with other matter, which collides with other matter, and so forth, as the disturbance is transmitted through the surrounding material. Mechanical waves can be produced and transmitted by matter in any form, solid, liquid, or gas. Table 15:1 lists several examples of mechanical waves, common sources of each, and whether these waves are transverse, longitudinal, or both. The various kinds of mechanical waves differ in the frequencies at which they commonly occur. If you count water waves as they strike the beach, you find that they rarely exceed a frequency of 1 per second, or 1 Hz. Earthquakes and jackhammers produce waves in the ground that range from 1 to about 50 Hz. Vibrations that produce sound audible to the human ear range from 20 to 20,000 Hz. Dogs hear sounds at still higher frequencies. We can arrange these frequencies in order from low to high, in a classification scheme called a wave spectrum. Figure 15:1 shows the wave spectrum for mechanical waves. Mechanical waves with frequencies below those of audible sound are called infrasonic waves and include the water waves and earthquakes discussed in the last chapter. Mechanical waves at frequencies. Wave classification 335. Approximate. Sivasp-Gorlinath. M. I.O. L vibrations of T plus 3x10. Atom seen solids. 10 He equals 10 co underscore 1043x10. 10 degrees plus. Hashtag I figure 15:1. 107, 4310 mechanical wave. Medical spectrum. E. Diagnosis. 10% sonic. Cleaning. 10%, 10 degrees, 10 degrees, 10 earthquake. Waves, 1 ocean waves, FO, tides. Table 15:1 Examples of mechanical waves. Water waves, objects thrown in water, transverse on surface. Wind-water interaction, diurnal below surface. Earthquake waves, sudden fault _. Sound vibrations of certain longitudinal objects, including Andvical, CL ord. Ultrasound vibrations of certain longitudinal objects, such as 6 bats vocal cords, and ship sonar. 336 Chapter 15. Waves, sound and electromagnetic induction energy transmitted. Coil. Figure 15:2. SIE. An oscillating spark at the left induces a similar oscillating spark on the right. Yes, spark. Oscillating electrical charges produce electromagnetic waves. 4E. High induced voltage spark H. Wire coil. Larger than audible sound are called ultrasonic waves. These waves have found wide application in industry, welding, cleaning, and detecting flaws in a variety of materials. Ultrasonic imaging is used in medicine, primarily in situations where X-rays are ineffective or dangerous. For example, ultrasound is used to examine the development of a fetus. Wavelengths, estimated from the media that usually transmit each kind of wave, are included in Figure 15:1. Electromagnetic waves. In the 1880s, Heinrich Hertz performed a series of experiments with electric ity and magnetism. Using a device called an induction coil, he became adept at producing vibrating electric charges, commonly called sparks, across an air gap. Near this oscillating spark, Hertz placed a coil of wire, which also had a Table 15:2 Examples of electromagnetic waves. Radio, television charges in an antenna transverse. Microwave molecules transverse. Infrared atoms transverse. Visible light atoms transverse. Atoms EET cray. Ultraviolet. X-rays electrons transverse. Gamma rays atomic nuclei transverse. Wave classification 337. Small air gap, Figure 15:2. Each time a spark occurred across the induction coil, a spark was produced across the wire coil as well. Energy had been transmitted from one coil to the other, although no mass had been transferred. Our interpretation of this phenomenon is that oscillating electrical charges produce waves. Light, television signals, radar, and microwaves are all examples of electromagnetic waves, waves created by vibrating electric charges. These charges can be a single charged particle like an electron or a chunk of electrically charged matter like an atom or molecule that has a net electric charge. One electric charge can affect another at a distance, even when there is no matter between them. Consequently, electromagnetic waves are transmitted through empty space as well as through matter. Light waves from the sun, for example, cross millions of kilometers of emptiness before reaching us. Table 15:2 lists several examples of electromagnetic waves and common sources of each type. As shown in the table, all electromagnetic waves are transverse. Electromagnetic waves range in frequency from less than 100 Hz, radio waves, to more than a million times this amount, Gamma rays. Figure 15-3 shows the complete electromagnetic wave spectrum. Visible light. Perhaps the most famous member of the spectrum, actually occupies an extremely narrow range of frequencies. It extends from the lower frequencies of red light, 4.5 x 10 Hz, to the higher frequencies of violet light, 7.5 10 Hz. Differences we perceive as color are, in fact, differences in frequency. Like mechanical waves, electromagnetic waves travel at different speeds in different materials. However, in a vacuum all electromagnetic waves travel at 3x 10 degrees meters per second, m/s, commonly called the speed of light. Wave lengths for electromagnetic waves in a vacuum are included in figure 15-3. Self-check 15a. Wave receivers. All waves transfer energy from a source to a receiver, but some receivers are more sensitive than others. Our eyes and photographic film detect visible light, but seem unaffected by the shorter wavelengths in microwaves. A television antenna absorbs the longer waves emitted by a television station but virtually ignores the shorter wavelengths of visible light. Microwaves can popcorn, while gamma rays cannot. To understand why receivers are more sensitive to some wavelengths than others, consider an example using water waves. Suppose you are sitting in a fishing boat that is 2 meters, m, long. While you are fishing, a water wave. 338 Chapter 15. Waves, Sound and Electromagnetic. Frequency wavelength. Hertz, meters. 10% asterisk IE 3 asterisk IO trademark. 3x10. 73 asterisk 10. 73 asterisk 10%. 3x 10%. 3x1 IO trademark. 3x10. 75x 50. Underscore 4 asterisk 107% M310. Violet. 3x10. XEOLPMELSXS 0% M3% asterisk 107. Green. Yellow. Figure 15-3 5410 L46 asterisk 107 M10 3x10. Electromagnetic wave orange infrared. Spectrum. T Diox 10 asterisk. Red 1 \3. 45 x 10 7 107 MAGS 10 degree. Microwaves. UE asterisk 107. Short radio. Waves mech. Underscore FM. And TV underscore. Short radio. AM radio. IES. 3% 10. A 310 degrees. Equals 44. Long radio ENE. Waves 2 asterisk 10 degree. With a wavelength of 20 m passes beneath you, figure 15-4, A. Your boat slowly rises and falls with the wave. Since the wavelength of the water waves is much longer than your boat, chances are your fishing will not be interrupted much. A wave with a 10 m wavelength will be only slightly more noticeable, while waves that are 4 to 5 m long will become apparent, figure 15-4, B. When the wavelength of the wave is approximately equal to the length of the fishing boat, fishing becomes virtually impossible, figure 15-4, C. The bow of the boat oscillates as every wave passes by. If the water waves become wave classification 339, wavelength equals 20 m. Figure 15-4. Wavelength equals 4 m. The closer the length of The boat is to the wavelength of the waves, the more easily it detects the waves. Wavelength equals 2m. Wavelength equals 0.5 m. Figure 15-5. Considerably shorter than the boat floats along the top of the crests. Figure 15-4, d, and the waves again pass unnoticed. You notice only the waves whose wavelength is close to the length of the boat. If we think of the fishing boat as an energy receiver, its behavior can be explained in terms of resonance. The bow of the boat oscillates more when the water waves push in time with its natural frequency. This natural frequency depends, in part, on the length of the boat. Consequently, waves that are about the same length as the energy receiver oscillate at frequencies near the natural frequency of the receiver. To be most effective, a wave detector needs to be about the same size as the wavelength of the waves it is to detect. Several examples are shown in Figure 15-5. 340 Chapter 15. Waves, Sound and Electromagnetic. Radio antennae are about 1 m long and detect waves that range from about 1 m to several meters long. Microwave detectors are at most a few centimeters long and detect waves of about the same length. When we proceed to electromagnetic waves of very short wavelengths, we cannot build detectors small enough. Fortunately, nature does. Infrared radiation is best detected by molecules. Visible light, with wavelengths of about 8x107 meters, is best detected by atoms. A similar analysis applies to mechanical waves. For example, the size of the eardrum is appropriate for the range of frequencies we call audible sound. The size of detectors is closely related to the size of the wavelength being received. Self-check 15b. Sound. Pleasant music soothes us, unexpected noises frighten us, the roar of the crowd excites us. Friends recognize us by our voices. Sound waves may well be the most familiar type of wave we experience. While sound is not the only way to communicate, it carries a large fraction of our thoughts, feelings, and opinions. We need only compare the social barriers faced by the deaf with those encountered by the blind to realize how much human beings depend upon this form of wave motion. Historically, sound was one of the first phenomena to which the wave model was successfully applied. The spread of sound in all directions from a source was likened to the spread of circular water waves from a pebble dropped into a quiet pond. Early interest in musical instruments contributed enormously to our understanding of standing waves and resonance. The concepts and images used to describe water and mechanical waves in a spring prove valuable in understanding the behavior of sound. Describing sound waves. A bell is placed inside a jar to which a vacuum pump has been attached. Initially the jar is filled with air and we hear the bell ringing. The jar is then sealed and the pump begins removing the air inside it. Gradually, the sound dies out. Although we can still see the clapper as it pounds away on the bell, we can no longer hear any sound. Sound requires a medium. Sound waves are longitudinal waves, capable of traveling through solids, liquids, and gases. We imagine atoms and molecules to be evenly spaced in matter, much like the evenly spaced coils in a spring. When a bell rings, its motion alternately compresses, squeezes together, and rarefies, pulls apart. The molecules in the surrounding air. A series of compressions and rarefactions travels through the air, figure 15-6, much as compressions traveled in the spring. Each molecule vibrates parallel to the direction in which the sound energy is transmitted. When the compressions and rarefactions reach your ear, they establish vibrations in the eardrum that are eventually transformed into nerve impulses sent onto the brain. The speed of sound has been measured in a variety of materials, some of which are listed in Table 15-3. Since wave speed depends on the medium, the speed of sound varies considerably in different materials. The speed of sound in air increases as the temperature of the air increases. At high temperatures, the air molecules move rapidly and transfer the wave energy to their neighbors more quickly than at low temperatures. Sound travels progressively faster as we move from gases to liquids to solids because of the stronger restoring forces. The stronger the molecular bond, the more rapidly the motion of one molecule influences the next. Sound waves travel most rapidly in solids. We describe sounds in terms of loudness and pitch. Loudness refers to our perception of the amount of energy carried by the sound wave. Consequently, it is related to the amplitude of the wave. As the energy carried by the sound wave increases, so does the amount by which molecules are compressed in each disturbance. Pitch describes how we perceive frequency or Table 15-3 speed of sound in various materials. Figure 15-6. A vibrating bell produces a series of compressions and rarefactions that travel to your ears. Gases, 0 degrees Celsius, A. Oxygen 316. Helium 965. Mercury 1450. Water 1498. Seawater 1531. Solids. Rubber 1800. Lead 2100. Glass 5000 to 6000. Granite 6000. 342 Chapter 15. Waves, Sound and Electromagnetic. At $_ Ness in frequency. Figure 15-7. And wavelength. The sound in C has a larger amplitude than the sound in B. The C and SY somes. Sound in A has a higher frequency and shorter wavelength than the sound in B. Differ in OI. Amplitude C equals 7YY XY Ren SE. Wavelength. A higher pitched sound has a higher frequency and shorter wave length than a lower pitched sound. Sound waves of differing amplitude, frequency, and wavelength are shown in Figure 15-7. Sound waves in matter. Hello, you shout as you stare up at the surrounding canyon walls. Hello. Comes the echo back to you. Hey, turn down that radio, comes a familiar yell. Funny how your neighbors always complain more in the evening than during the day. I can't hear you through that ski mask, you tell a friend as you get on the lift. Like water waves, sound waves can be reflected, refracted, and absorbed as they move from one material to another. Reflected waves have the same wavelengths as incident waves, but they Travel in the opposite direction back toward the energy source. Echoes reveal these characteristics. Your echo sounds similar to your voice, its energy is simply traveling back toward you rather than away from you. Sound can be reflected from any hard surface, from the walls in a hallway as well as the walls in a canyon. However, your ear can distinguish the echo as being sepia rate from the original sound only when the original and reflected waves reach your ears at least 0.1 seconds apart. In most buildings, the reflected waves reach your ear more quickly. Consequently, the reflections mix with the original waves, contributing to what we call the brightness of a sound instead of producing an echo. A less well-known application of sound reflection is the use of curved surfaces to focus sound. Figure 15-8 shows waves reflected by a curved barrier. Energy carried by the entire wave front is reflected to a single point, called the focal point. Sound waves behave in much the same fashion, Fig. 15-9. Curved surfaces used in a directional microphone focus the incoming sound waves, allowing the microphone to pick up more sound. Ears, both. Sound 343. Figure 15-8. Waves reflected from a curved surface can be focused to a single point, called the focal point. Figure 15-9. Directional microphones and ears take advantage of curved reflectors. Microphone E equals underscore H, A. 344 Chapter 15. Waves, sound and electromagnetic. Cooler. Warmer. Figure 15-10. Sound waves are refracted, A. Upward ground during the day and B. Downward at night. Cooler ground. Human and animal are shaped to focus as much sound as possible on the eardrum. In outdoor amphitheaters, orchestras are often placed in front of a curved reflecting surface to direct more sound back toward the audience. Since the speed of sound in air varies with the air temperature, sound is often refracted by the atmosphere. During the day, the air near the ground is warmed more than the upper levels. Since sound travels more quickly in warm air than in cool air, sound waves are gradually refracted upward, figure 15-10, A. At night, the reverse occurs. Air near the ground cools more rapidly, and sound waves are refracted downward, figure 15-10, B. Refraction N. Enables sound to travel farther along the ground at night than during the day. There is an explanation for your neighbor's complaints. Waves are absorbed when the energy stored in the disturbance is dissipated into thermal energy found in the motion of molecules within matter. Those sound waves are easily transmitted through air. Pockets of air within solids act as extremely effective sound absorbers. Sound waves enter the pockets of air, only to be reflected back and forth by the solid boundaries enclosing the air pockets. Eventually, the organized vibrations of the wave become the disorganized motions of the air molecules. Sound has been absorbed. Acoustic tiles designed to muffle room noise are made from porous foam or loosely woven fibers that create many such air pockets. Rugs and foam rubber are also excellent absorbers of sound. Architects take the absorbing properties of materials into account in designing buildings and concert halls. Music and standing waves. A small necked bottle stands under a dripping water faucet. Each time a drop hits the bottle, it makes a sound. When the bottle is empty, the pitch of the sound is low, but as the bottle fills up, the pitch becomes higher. As the air space above the water shortens, the pitch of the sound rises. Sound 345. Figure 15 to 11. Figure 15 to 12. Which instrument, as the string gets shorter, the wavelength produces lower associated with the fundamental frequency. Frequency sounds decreases. The shorter the string, the higher the pitch produced. Musical instruments display the same relationship between length and pitch. Without ever hearing them, you know that the instrument on the left in Figure 15 to 11 can play lower notes than the one on the right. Within a family of instruments like the string family, the longer bass viols have a range that extends much lower than the shorter violins. This relationship between the size of the instrument and pitch can be explained in terms of standing waves and resonance. Consider how different pitches are produced on a single string. To vary the pitch of a string, a guitarist presses the string against the guitar neck at different points, thereby changing the length of the string that is free to vibrate when plucked. A guitar string vibrates in much the same way as the spring we discussed in chapter 14. Both ends of the string are fixed, one at the bottom where the string is tied off and the other wherever the guitarist places his or her finger. When the guitarist plucks the string, standing waves are produced at the resonant frequencies characteristic of that length string. These standing waves cause the wooden body of the guitar to vibrate, causing the air within it to vibrate, and eventually causing a sound wave to be transmitted to your ears. The sound we hear can ultimately be traced back to the standing waves possible in the guitar string. The fundamental frequency produced in a guitar string varies with the length of the string, figure 15 to 12. Since 1/2 of a standing wave is the 346 chapter 15. Waves, sound and electromagnetic. Minimum wavelength that can fit in each length of string, the wavelength associated with the fundamental frequency is twice the length of the string. As the string gets shorter, this wavelength gets shorter. Since frequencies increase as wavelengths decrease, short strings must have higher fundamental frequencies than longer strings, as the guitarist moves his or her fingers along the neck of the guitar, he or she lengthens and shortens the string to produce the desired pitch. Self-check 15C. X fundamental. X wavelength. Figure 15 to 13. The analysis can be extended to wind instruments, trumpets and sosaphones, for example, are long tubes that for convenience have been folded up about themselves. Air inside the tubes can be made to vibrate in a standing wave pattern with a node at the mouthpiece end and an antinode at the bell. Valves are used to change the lengths of the air columns. Since trumpets are made from much shorter tubes than sosaphones, their range of frequencies extends higher. While the fundamental frequency in a violin string or air column is the dominant pitch we hear, other pitches are often present simultaneously. In a violin string, for example, the only constraint on the standing waves is that they have nodes at each end. A number of different frequencies satisfy this requirement. When a string vibrates, many frequencies are produced simultaneously but at different amplitudes. These vibrations are picked up by the wooden sound box, which further augments or diminishes their amplitudes to produce a sound wave in air that is relatively complex. Figure 15 to 14 contrasts the contributions of the lowest two frequencies for a violin and piano when each is playing the A above middle C. These different contributions lead to significantly different waveforms, figure 15 to 15. While pianos and violins can play the same pitch, they do not produce the same sound waves. Differences in the higher frequencies establish the quality of the sound, the characteristic that enables us to distinguish one instrument from another. The sound of a siren. As the ambulance speeds by, its siren goes from a higher pitch to a lower one. Our most common experience with the Doppler sound 347. Figure 15 to 14. EI and Domenta. The sound we hear XNEANS depends on the amplitude of the fundamenta. Harmonics. For a cos violin, the amplitude of the second harmonic is conde, the same as the funda. On mental. For a piano, the amplitude of the second harmonic is tiny compared to the amplitude of the fundamental. These differences produce two very different looking waves. Violin, piano. Figure 15 to 15. Two very different looking waves lead to two very different sounding sounds. Here the piano and violin play the same pitch. Effect occurs with sound. A drawn-out note like an ambulance siren or train. Figure 15 to 16. Whistle changes pitch as it travels past a stationary observer. Compared to the frequency of the single note it produces when the ambulance is stationary, the siren sound we hear depends on the velocity at which higher as the ambulance approaches the observer and lower as it moves away the ambulance travels from the observer. Like the water waves described in chapter 14, sound waves are affected by the motion of the source or receiver. As the source moves toward the receiver, the sound wave compressions become more closely spaced and the receiver hears a higher pitch than that being emitted by the source. As the source recedes, the compressions are more widely spaced, and the receiver hears a lower pitch, figure 15 to 16. The frequency of the sound we hear depends on the relative velocity between the source and ourselves. 348 Chapter 15. Waves, Sound and Electromagnetic Love hearing that lonesome wail of the train waste as the AIIGUNODEVE. The frequency of the wave changes due to Tre-Dorium effect. Copyright 1980 by Sidney Harris. Electromagnetic waves. All wave motion is defined as the transfer of energy without the transfer of matter. Nevertheless, mechanical waves do depend on the presence of matter. A bell clanging in a vacuum produces no sound. Electromagnetic waves are different. They do not depend on matter for their existence. Light is transferred continuously between the sun and the earth. Radio and television signals provide astronauts a link with home. X-rays, gamma rays, visible light, and radio waves continually bring us messages from the stars, crossing an emptiness more vast than we can imagine. Describing electromagnetic waves. Electromagnetic waves are created by vibrating electric charges. A vibrating electron can induce vibrations in another electron, which in turn induces vibrations in yet another electron, and so forth. Energy, but no mass, is transferred from one electron to another. Because electrical interactions occur at a distance, this energy can be transferred across empty space, as well as across matter. Electromagnetic waves are very hard to imagine. To provide a medium analogous to water for water waves or air for sound waves, physicists use the concepts of electric and magnetic fields. Electrically charged objects create an electric field around themselves. This field describes their ability to influence other charged objects across empty space. When the object vibrates, it produces a disturbance that moves through this electric field, much as a water wave moves across water. When the disturbance in the field reaches another charged object, it can induce that object to vibrate. In a sense, electric fields provide us with a way of picturing the empty space surrounding the charged objects and the way in which energy can be transferred between them. Electromagnetic waves 349. Figure 15 to 17. Two fields, one electric and the other magnetic, vibrate at right angles to one another as an electromagnetic wave is transmitted in the third direction. All electromagnetic waves are transverse. Electromagnetic waves are actually a result of both electric and magnetic fields. A moving electrical charge produces a magnetic field and an electric field. This magnetic field can influence another moving electrical charge in yet a different way than the electrical field. Consequently, two disturbances are actually propagated, one through the electric field and a second through the magnetic field. Physicists picture electromagnetic waves in terms of changes in these two fields, as illustrated in figure 15 to 17. The energy transferred by the wave travels perpendicular to the direction in which either field vibrates. All electromagnetic waves are transverse. In a vacuum, all electromagnetic waves travel at the same speed. 3x 10 degrees m/s, or 186,000 miles per second. In matter, electromagnetic waves travel at somewhat lower speeds. Like sound, light travels at different speeds. In air at different temperatures. Representative speeds are included in table 15 to 4 for distances on Earth. These speeds are enormous. Consequently, electromagnetic waves seem to us to travel instantaneously from one point to table 15 to 4 speed of light. In various materials, vacuum 2.998 x 10 degrees, liquids 20 degrees Celsius, water 2.250 10 degrees, glycerin _2.040 x 10 degrees, carbon disulfide 1.840 x 10 degrees, solids equals, i.e. 2.290 x 10 degrees, quartz 1.940 x 10 degrees, crown glass 1.970 x 10 degrees, diamond 1.240 x 108. 350 Chapter 15. Waves, Sound and Electromagnetic. Another. We can measure the time it takes for a thunderclap to reach us, but the lightning flash appears to take no time at all. Only when we look at distances as large as those between planets, stars, and galaxies does the finite speed of electromagnetic waves begin to take on meaning. Light from the moon reaches us in a little over a second, light from the sun, in about 8 minutes. Self-check 15D. Light in matter. Our young son has just realized that there is not another baby in the mirror. He reaches out and finds the cold hard surface of the glass rather than the soft skin he expected. The hiker has just realized that the lake in the distance is a mirage. With each step he takes, the lake fades farther into the distance. You left your bicycle in the sun again, its black seat is hot. Reflection, refraction, and absorption describe the behavior of electromagnetic waves as effectively as they describe waves in sound and water. We see most objects by virtue of reflected light. Light from a lamp strikes the table, for example, and is reflected to our eyes. Light waves moving parallel to one another before striking the table are reflected in all directions, figure 15 to 18. Within this apparent chaos lies the information our brain system uses to tell us that we are looking at a table. Light reflected by each point along the table's surface obeys the law of reflection. The angle of reflection equals the angle of incidence. The uneven, bumpy surface of the table offers a different angle of incidence at each point. Consequently, the pattern of reflected waves carries information about each and every point on the table's surface, information we learn to interpret in a fraction of a second. Figure 15 to 18. The bumps in the reflecting surface affect the way in which parallel rays of light are reflected. Each surface creates a unique pattern of reflected waves. Table WG. Electromagnetic waves 351. Figure 15 to 19. Mirror surfaces are so smooth that parallel rays of light remain parallel to one another. After reflection, the mirror imposes no pattern of its own on the reflected light. Mirror. Figure 15 to 20. Our eyes trace light along straight lines. A light ray reflected by a mirror appears to have come from behind the mirror, as shown by the dotted line. We see an image that appears to be behind the mirror. Mirrors allow us to see the baby instead of the mirror because they make little impression of their own on the light waves. Light waves moving parallel to one another before striking the mirror are still parallel once they are reflected. Figure 15 to 19. The mirror surface is so smooth that it imposes little, if any, pattern on the light it reflects. Consequently, light that has first been reflected by a baby will still carry information about the baby when it is reflected by the mirror. We see the baby instead of the mirror. The information reflected by the mirror creates an image of the baby that appears to be located behind the mirror. This arises from the way we interpret light's motion. Experience with light sources has led us to expect light to travel along straight lines. Figure 15-20, A, shows one path the light waves travel as they strike the baby's head and are then reflected by the mirror. As we gaze into the mirror, the reflected light seems to travel along a straight line path that originates behind the mirror, as shown by the dotted line. Our eyes trace that straight line path, not the real path traveled by the light. Light waves traveling along paths that diverge from a single point on the baby's head appear to be diverging from a point behind the mirror. Figure 15-20, B. The image we see is formed at that point. The same is true for light. Emerging from all other points along the baby's body. Thus, a complete image is formed behind the mirror. Only with experience do we come to realize that we are seeing just an image and not the real object. 352 Chapter 15. Waves, Sound and Electromagnetic. Figure 15 to 21. Light is refracted as it strikes the glass surface. Figure 15 to 22. Of a prism. Light is refracted toward the normal as it enters the medium. Figure 15 to 21 shows several narrow beams of light as they strike a prism. A small part of the light is reflected at the glass surface, but most is transmitted into the prism. Light that is perpendicular to the surface continues to travel along the same path. Light incident at other angles, however, bends. Light, like sound and water waves, is refracted as it moves from one medium to another. You have seen this phenomenon often in swimming pools. The submerged part of your body looks shortened, due to the bending of light as it emerges from the water into the air. Like other wave phenomena, light waves are refracted due to the change in wave speed that occurs as waves enter new media. Light travels more slowly in glass than in air. If we trace a single beam of light, figure 15 to 22, we see the light refracted toward the normal as it enters the medium, and away from the normal as it moves back into the air. Light waves, however, display a characteristic called dispersion. The speeds at which light waves move in matter depend on their wavelengths. The differences are small, but sufficient to refract each wavelength of light at a slightly different angle. White light, a mixture of all wavelengths, is separated into its colors. Red light. Electromagnetic waves 353. Is refracted the least, violet light, the most. If we replace the prism with a figure 15 to 23 drop of water, we have a rainbow. Mirages are formed. Like sound, light waves experience atmospheric refraction due to the when light from the sky. Fact that the speed of light in air increases as the temperature of air increases. Is refracted upward by warmer layers of air. Mirages are caused by this refraction. Air near the surface of hot sand is our eyes trace the warmer than the air above it. Light traveling downward from the sky is re-refracted light along. Fracted as it encounters warmer layers, until its path is actually bent back straight lines, creating an image that appears upward, figure 15 to 23. Hikers see this reflected light and trace its path back to be located on the ward along a straight line to the ground. Seeing an image of the sky on the ground in front of us, they naturally assume it is a reflection from the surface of a lake. Drivers see the same effect as they drive along asphalt highways on hot, sunny days. Electromagnetic waves are absorbed when the energy stored in the electromagnetic disturbance is dissipated into thermal energy. The hot bicycle seat provides us evidence of how effectively this process can occur. Infrared radiation and visible light have wavelengths that correspond roughly to the sizes of atoms and molecules. Consequently, the energy stored in and transmitted by these electromagnetic waves is easily transformed into the thermal energy associated with the motions of atoms and molecules. In Chapter 10 we called this process radiation absorption. 354 Chapter 15. Waves, Sound and Electromagnetic. TTC Seeing the bait. In 1916 William Dinner. The law of restraint on would not. Ziegler thought of a flexion tells us that see their own reflex. Way to use the law of the angle of insertions. 1 must 1. Reflection to catch it and equals the der, then, about y. Fish. His artificial fish angle of reflection, Mr. Ziegler put the bait looks similar to so fish approaching hooks on the back. Many others accept the mirror from any and bottom of his. For the mirror, 5, in angle other than bait. The middle. A fish. A. Would swim near the bait and see its own reflection. Thinking iOS. That another fish is 7I225. OO. EI2.2933. Would grab the bait. J. Before it could, the if fish would bite, thus becoming someone's standing waves in microwave ovens. Oops, you forgot to take the casserole out of the freezer. Guess you will have to use the microwave oven. You shove the casserole in, close the door, set the timer, and push the button. 20 minutes later it is done. Steam rises as you lift the casserole out of the oven. You take a huge helping from the center and take your first bite. Ugh! It is still cold. A quick check shows that the casserole is plenty hot around the outside but still cold in several spots near the center. What happened? Microwave cooking, one of the more recent additions to kitchen technology, is based on the principle of wave absorption. Microwaves, with a frequency of about 210 degrees Hz, stimulate the water and fat molecules in foods to vibrate. The thermal energy generated by these vibrations cooks the food, often in a fraction of the time required in a conventional oven. Glass and plastic containers, as well as the surrounding air, absorb very little of the energy carried by the microwaves, so most of the energy goes directly into the food being cooked. One of the major disadvantages, however, has been the uneven cooking typical of many oven designs. You can understand this uneven cooking in terms of standing waves. Microwaves generated by most microwave ovens have a wavelength of about 13 centimeters. Consequently, 3 to 4 complete wavelengths can fit into the oven cavity. To prevent leakage of microwaves to the outside, the oven's interior is lined with metal, which is an excellent reflector. The waves emitted by the microwave source interfere with the waves reflected from the sides, and a standing wave pattern is produced. Energy is distributed unevenly. Electromagnetic waves 355. 4.0 x 107 m 7.5 x 107 m. Figure 15 to 24. Violet light emitted by each chemical element has a light spectrum characteristic of that element. About the oven's interior, with most of the energy concentrated at antinodes, and little energy located at nodes. Your casserole's cold spot was located at a node. Because of safety concerns, metal interiors are likely to remain an essential feature in microwave oven design. It would therefore be impractical to try to eliminate standing waves. Most recipes suggest rotating the food once or twice during cooking, thus rotating areas from nodes to antinodes for more even energy absorption. Some manufacturers have added rotating platforms that move the food continuously as it is being cooked. A second solution is to move the standing wave pattern itself. A rotating microwave source produces a standing wave pattern that moves about the food, moving nodes to different sections of the dish. Rotating fans have also been used. These fans reflect microwaves in continually changing directions, so that the standing wave patterns change as well. The expanding universe and police radar. Electromagnetic waves, like mechanical waves, experience a shift in apparent frequency when either the source or the receiver is moving. This electromagnetic Doppler effect is used to measure the speeds of objects that are approaching or receding from us, objects as diverse as galaxies and automobiles. For more than a century, astronomers have analyzed the light emitted by stars. The visible light emitted by a glowing gas, such as hydrogen or helium, is a mixture of different wavelengths. Each gas has its own characteristic mixture. When the light is passed through a prism, the different wave lengths are separated, creating a pattern characteristic of that gas, called its line spectrum, figure 15 to 24, by comparing light from stars and galaxies. With the spectra of known gases, astronomers can tell what chemical elements are present. Astronomers found perplexing data when they analyzed light from very distant stars and galaxies. A spectrum would show all the lines characteristic. 356 Chapter 15. Waves, Sound and Electromagnetic. Figure 15 to 25 Laboratory. Light emitted by distant stars and galaxies. 656.3 x 107% m. Shows shifts in frequencies characteristic of the Doppler effect. Spectrum. Astronomers believe from a star that these shifts arise from the motion of stars 657.5 x 10 m and galaxies outward from the origin of the Big Bang of hydrogen, for example, but the lines were uniformly shifted to lower frequencies, figure 15 to 25, described in terms of wavelength. The lines were shifted toward the red end of the spectrum, thus the effect was called the red shift. The red shift is consistent with a model of the universe in which all galaxies are moving outward, away from one another. Like the sound of a train whistle, as the train moves away from you, light is shifted toward lower frequencies as galaxies recede from us. A more down-to-earth illustration of the electromagnetic Doppler effect is police radar. A police officer who wants to measure the speed of a car uses the shift in frequency of radar waves reflected by the moving car. Because of the car's motion, the reflected waves are shifted compared to the frequency. Reflected waves emitted by the radar unit, figure 15 to 26. By comparing the frequency of the are shorter radar emitted by the antenna with the frequency of the reflected waves, a any computer built directly into the radar system can calculate the car's speed. As the car's speed increases, so does the magnitude of the shift in frequency. From police. When the police car is stationary, the frequency change provides all the reflected waves are longer. Required information with which to calculate the car's speed relative to the ground. When both cars are moving, however, the frequency shift allows calculation only of the relative speed between the two cars. In order to deter P equals crapr waves mine the car's speed relative to the ground, moving radar units emit 2 sig. FEOM police. nals. One is reflected by the moving car, allowing the radar unit to calculate. Figure 15 to 26 the relative speed between the two cars. The second signal is reflected by the police radar measures road and allows the radar unit to calculate the police car's speed relative to the speed of cars by the ground. Given the two speeds, the computer can calculate the car's speed. Looking at the shift in relative to the ground. From galaxies to automobiles, the Doppler effect AL. Frequency of radar. Waves reflected by the allows us to measure the relative speed between objects. Moving car. The success of the wave model in describing a wide range of phenomena is indeed impressive. Starting with waves in springs and waves in water, we have been able to build mental pictures of sound and light waves. We cannot see the vibrations of atoms and molecules that combine to produce sound, but we can understand how sound behaves in terms of these vibrations. Wave reflection, refraction, and superposition provide an effective way of understanding echoes, sound transmission at night, and the design of musical instruments. We cannot see the electric and magnetic fields whose motions create electromagnetic waves, but we can understand how light, radar, and micro waves behave in terms of waves. Chapter 16 examines two additional wave phenomena: diffraction and interference, and their role in convincing physicists of the wave nature of light. Electromagnetic waves 357. G middle cent. Right off the end of the piano. It electromagnetic radiation could be nearby galaxy emitted by playing a piano, the visible distant galaxy spectrum would occupy quasars about 1 full octave. The Doppler shifts EEEEGEAE background radiation observed by astronomers can be huge, literally taking us right off the end of the piano. Red shifts have proven enormously useful to frequency of 256 Hz. The C below middle C has astronomers providing what seems to be profound a frequency of 128 Hz. In the electromagnetic evidence in support of the Big Bang model of the spectrum, visible light has a range equivalent to universe, see Chapter 8. As we look deep into about 1 octave, 410 Hz to 8x10 Hz space, the extent of the red shift becomes above and below this octave, we would find the staggering. It is hard to appreciate the size of other forms of electromagnetic radiation. These shifts, however, without a benchmark, a reference frame for comparison. Fortunately, consider the red shifts observed by astronomers. The piano provides a useful analogy. Beginning close to home, nearby galaxies emit light that is redshifted about 1 step or so. Suppose that a train whistle emits a pitch light drops in frequency by 1 note on R, corresponding to middle C on the piano, as electromagnetic piano. As we progress to more, the train moves away from us at 25 m/s, 90 distant galaxies, the red shift becomes larger. The kilometers per hour, its whistle sounds about 1 farthest galaxies that have been observed so far. Half step, 1 note, lower to us than the sound have a red shift equivalent to the change of an emitted by the train. We hear B below middle C octave. These shifts indicate that distant galaxies. For sound, this shift is one of the larger Doppler are moving away from us at speeds of about shifts we encounter. Most are far less. To hear a 6x10 m/s If we look still deeper in space, the shift of a full octave, for example, the train would most distant quasars have red shifts equivalent to have to move about 500 kilometers per hour. A couple of octaves. They are moving away from. Most ordinary objects do not move at such high us at enormous speeds up to 90% of the speeds. For astronomers, however, Doppler shifts of light can be this large or even larger. Let's compare their observations with the more familiar in 1965 Arno Penzias and Robert Wilson detected shifts observed for sound radio waves that seem to come from even deeper in space. This radiation is coming to us. We do not normally think of electromagnetic from all directions, so we call it background radiation in terms of octaves. However, for radiation, its red shift is so large that it falls right. Comparisons involving the Doppler shift, such off the end of our piano, presumably released at a construct, is quite useful. A musical octave the time of the Big Bang itself, this radiation and ranges from one frequency to twice that. Its red shift hold clues to events that occurred in frequency. Middle C, for example, has estimated 20 billion years ago. 358 Chapter 15. Waves, Sound and Electromagnetic. Chapter Summary. Wave phenomena can be separated into two categories: mechanical waves and electromagnetic waves. Mechanical waves are produced in matter in any form: solid, liquid, or gas. One piece of matter is displaced and the disturbance is transmitted throughout all parts of the surrounding matter. Electromagnetic waves are produced in empty space as well as in matter. Vibrating electrical charges produce disturbances that are transmitted across space. By ordering waves according to frequency, the wave spectrum organizes the different types of waves within each category. Mechanical waves include water waves, earthquake waves, and sound waves. Sound waves are longitudinal waves. Displacing one atom or molecule produces a series of compressions and rarefactions that are transmitted by the surrounding matter. We use the terms loudness and pitch to describe our perceptions of the amplitudes and frequencies of sound waves. Sound waves are reflected in echoes, refracted by the atmosphere, and absorbed by trapped pockets of air. All musical instruments are designed to produce standing waves that establish the pitch and character of musical sounds. The lengths of the vibrating strings or air columns determine the fundamental frequencies. The fundamental frequency establishes the pitch. Higher harmonics contribute to the character of the sound. Sirens and train whistles provide daily examples of the Doppler effect. Electromagnetic waves can be described as disturbances in the electric and magnetic fields that surround a moving electric charge. Light, radar, and microwaves are three of the many kinds of electromagnetic waves. They differ from one another in frequency. Different colors of light have different frequencies as well. Light can be reflected, refracted, and absorbed by matter. The light reflected from objects to our eyes allows us to see the objects. Reflections from very smooth surfaces give rise to mirror images. Atmospheric refraction leads to the formation of mirages. Absorption of light and infrared radiation leads to the process of heat transfer called radiation absorption. Absorption of microwaves is used to heat food in microwave ovens. Reflected waves in microwave ovens produce standing waves, resulting in uneven cooking. The electromagnetic Doppler effect is used extensively in measuring speeds of galaxies as well as speeds of cars. Answers to self-checks. 15a. Human speech involves frequencies around 200 to 400 Hz. Microwaves include frequencies from 10 degree - 10 Hz. Human speech involves mechanical waves. Microwaves are electromagnetic waves. 15b. AM waves have a lower frequency, and hence a longer wavelength than FM waves. To be effective, an energy receiver needs to be about the same size as the waves it is to detect. Since AM and FM waves have different wavelengths, the radio antenna will need to be adjusted differently for best reception of each range. The antenna will have to be longer for AM reception. Problems and questions 359. 15ca. The fundamental frequency will have a wavelength that is 4 times the length of the air column. B. As the bottle fills up, the length of the air column shortens. Consequently, the fundamental frequency will have a shorter wavelength, and hence a higher frequency. The pitch of the sound goes up. Tiny e distance 40 to 10%. M. 15d equals 1,4 x 10s. Speed of light 3 x 10 degree m/s. 1 year is equal to 3.2 x 10s, so about 4.4 years have elapsed since the message was sent from Alpha Centauri. 15e. The furniture wax fills in the low spots in the wood grain, producing a much smoother surface. As the surface becomes smoother, light waves are reflected more regularly and an image is formed. Problems and questions. A review of chapter material A12. Describe how the Doppler effect allows us to measure the speed of distant galaxies. Al. Define the following terms, and passing automobiles. Mechanical waves. Wave spectrum. Electromagnetic waves. A2. Give examples of mechanical waves and B. Using the chapter material. Electromagnetic waves. A3. Describe how the size of a wave receiver is BL. In chapter 14 we studied waves related to the wavelength of a wave. X springs. Are these waves mechanical or plane? The reason for this relationship. Electromagnetic. Explain how you reached A4. Describe the differences between your conclusion. Cal and electromagnetic waves. B2. Cyclotron radiation is a type of wave as. Describe how a curved surface can focus dujade by electrons that are traveling in a waves circle. Is cyclotron radiation a mechanical? A6. Use refraction to explain why sound or electromagnetic wave. Explain how you Els further along the ground at night then reached your answer during the day. B3. One way in which astronomers study the A7. Explain how the frequency of a sound universe is to detect radio waves emitted. Wave is related to the size of the wave by the hydrogen molecule. The wavelength source of this wave is 0.21 m. Would you expect? A8. Explain how the Doppler effect is related the astronomers' detectors to be larger or to the changing pitch of a siren as it passes smaller than AM radio antennae. Why? At high speed. B4. A microphone is a detector of sound. AQ. How are electric and magnetic fields used? Would you expect the size of a microphone to describe the motion of electromagnetic to be greater, smaller, or approximately the waves. Same size as the human ear? Explain. Al 10. Use the law of reflection to show how in B5. A supernova is the explosion of a star. If a image is formed by a mirror, supernova occurs somewhere in space, will all. Why do standing waves affect microwave sound from it be detected on Earth? Can cooking light from the supernova be detected here? 360 Chapter 15. Waves, Sound and Electromagnetic. E. Air. Water. See extensions to new situations. GL, when lightning occurs, it creates two types. B6. Medieval musical instruments called crumb of waves sound and light. Because these horns are shown above. One is an alto, the waves travel at different speeds, there are re. Other is a higher pitched soprano. Using vowel times can be used to estimate the dis. Physical principles, describe why you can dance to the lightning flash. Light travels at. Determine which is the alto. 3x 10 degrees m/s and sound moves at about. B7. Sound can be heard across a still lake 300 m/s. Suppose we hear thunder about. Much better than across a lake which has 2s after we see the lightning flash. Lots of waves. Apply reflection of sound to a. How far does sound travel in 2s? Explain why. B. How long would it take light to travel? B8. A car is traveling down the road with its the same distance. Horn blaring. What would you need to see approximately how far away did the know so that you could measure the car's lightning flash occur? Speed from the Doppler shift of the horns d. Can you make up a general rule to d? Sound. Determine the approximate distance to a. B. What frequency of electromagnetic wave flash of lightning would be produced by electrons vibrating C2? The sitar, an Indian musical instrument. At 60 Hz, 120 Hz, 240 Hz. What wood has a number of strings that are never? Be the speed, in a vacuum, of each of these plucked by the player. These strings are electromagnetic waves, called sympathetic strings and are identical. B10. Each of the light waves shown below is to strings that are plucked. Use the idea of striking a mirror as shown. Draw the direct resonance to explain why the sympathetic tion of the reflected wave strings vibrate and produce music, even though they are never touched by the sitarist. C3. Could you ever sing and cause a stringed instrument to sound even though you do not touch it? Explain how and why. C4. In a television commercial for a particular brand of audio tape, a recording of a singer is shown shattering a wine glass. Use the concept of resonance to describe how one can shatter glass with sound. BLL light travels more rapidly in air than in C5. The speed of electromagnetic waves is water. Draw the direction of the light waves used to define astronomical distances. The in water for each of those shown in air in distance that light, or any other electro. The next column. Magnetic wave, travels in 1 year through. Problems and questions 361. Copyright 1973 by B. This frequency must be all around us. Sidney Harris. Because of all the wires. Why do we not normally receive it on our radios and televisions. C8. Each of our hearts contains a natural pace maker, which stimulates our heart to beat about 60 to 80 times per minute. If this natural method fails, an electronic pace maker can be inserted. The electronic device detects electromagnetic nerve signals in the heart. If no signal is detected, the electronic pacemaker fires. Why could it be dangerous or fatal for an electronic pacemaker to be near sources of strong electromagnetic waves, like microwave ovens? C9. Your neighbor is playing music rather loudly, so you close your windows. Now, you hear only the bass portion of the music. A. What size objects will vibrate in resonance with the bass? B. What objects of this size are between you and the music? C. Would you expect these objects to as unspecified, they want an imioveranlui vibrate at high or low frequencies? Onui rove % the message was sent out 3 million years ago. D. Why do the bass pitches but not the higher pitches reach you when the window is closed? C10. Astronomers have looked carefully at the empty space is called a light year. The spectrum of light emitted by the Sun. The nearest star, Alpha Centauri, is for light have discovered that rays of light from years away. Edges A and B have shifts in their frequency. A. How far away is Alpha Centauri in size? The frequencies emitted at A are kilometers greater than normal, while those from B. In 1974 the radio telescope at Arecibo, are less. Puerto Rico, sent a message toward a star cluster called M13, which is 27,000 light-years away. Within a day the following telegram arrived at Arecibo. Message received. Help is on its way. M13. Why did the astronomers think this message was a prank? C6. Suppose a movie set has a mirror on it. You wish to take a picture of the actor's image in the mirror but do not want images of the camera, lights, or crew. How should you arrange the mirror, actor, lights, and camera? CI, alternating current in the United States A. Which side, A or B, is moving toward? Oscillates at 60 Hz, the Earth. A. What frequency electromagnetic wave B? Which side is moving away from the is produced around your lamp cord? Earth. 362 Chapter 15. Waves, sound and electromagnetic. See what do these measurements tell you? D. Use the equations for relative velocities about the sun's motion in Chapter 3 to determine if the driver ch. In Chapter 14 we stated an equation for of the car deserves to be cited for the frequency shift of a wave emitted by a speeding moving source. This equation is used to cal C12. Singing in the shower has long been known. Calculate the speed of a car from which police to change the sound of one's voice. Radar has been reflected. For this problem, paired to singing in an auditorium, we can rewrite this equation as, A. What range of frequencies would you expect to be enhanced by resonances in speed of car equals the shower room speed of light, change in frequency, B. In terms of energy output, why is it frequency of radar particularly useful to enhance these frequencies? Suppose a radar unit has a frequency of 10 degrees Hertz. D. Activities. A. What are the speeds of cars that cause frequency shifts of 100 Hz, 300 Hz? D1. If you can borrow an oscilloscope, look at 700 Hz, 1000 Hz. The interstate the waves produced by your voice or speed limit equivalent is about 25 m/s. Music. B. When the radar unit is moving, the D2. The next time you are in the bathroom. Speed of the car is actually the relative Singer scale. Can you identify the resonant speed between the car and the radar frequencies of the bathroom unit? With the frequency shifts in part D3. Visit a stereo store and learn how the A. Increase or decrease if the car were signers of the store considered resonances. Traveling east and the radar unit were in designing the speaker demonstration. Traveling west? Explain. Room. C. When moving radar is used, 2 FRED4, the next time you close your window 2 frequency shifts are measured. 1 FRE keep out your neighbor's loud music, place. Frequency shift is measured from radar your hand on the wall or window. Can you? Waves reflected from the moving car. A. Feel it vibrate. Second frequency shift is measured D5. Tune your radio to a distant station. From radar waves reflected from the change the antenna length until you find road. Suppose that the car and radar the best reception. Is this length different? Unit are moving in opposite directions. For FM and AM reception? The frequency shift measured from RAD6. Investigate different brands of microwave. DAR waves reflected from the moving ovens. Ask a salesperson to explain how. Car is 750 Hz and the shift reflected the ovens avoid standing waves, usually. From the road is 500 Hz. What is the called hot spots, and how they keep the speed of the car relative to the radar energy inside the oven? Listen to the sales unit. The speed of the radar unit rela pitch carefully. Then evaluate the sales tip to the road. Person's knowledge of physics.